We've already learned how to add vectors that are parallel or perpendicular to each other. But what if the vectors aren't parallel or perpendicular? Just like these two vectors that you see here, the green and the pink. These two vectors are definitely not parallel, and they're not perpendicular either. Let's take a look at what these vectors look like if we put them on an xy axis. If I wanted to add these two vectors graphically, I would need a perfectly scaled xy axis, just like I have here, and then I could draw the resultant. Again, I've put these two vectors tip to tail, and so I can draw my resultant. My resultant goes tail to tail and tip to tip, just as this vector here. Looking at my perfectly scaled xy axis, I can count how many units it is in the x direction and how many units it is in the y direction. 2, 4, 6, 8, 10, 12, 14 units. So the x component of this vector is 14. The y component of this vector is 2. When you have an x component and a y component, you should be able to find the resultant, because this is just like adding two perpendicular vectors. But we're going to learn how to do it when we don't have a perfectly scaled xy axis. There are 5 steps to follow for adding any vector. Go ahead and pause the video and take a few minutes to write down these 5 steps. We will use these 5 steps in a couple of example problems so you can understand exactly how to use them and so that you can become comfortable using them. Our first example problem talks about a man named Sudhir who walks 0.4 kilometers in a direction 60 degrees west of north and then goes 0.5 kilometers due west. It wants to know what his displacement is. Before we follow those 5 steps, we're actually going to draw a diagram showing these displacements. It says that he first walks 0.4 kilometers 60 degrees west of north. If I draw an axis that shows my north, east, south, and west, my vector that is 60 degrees west of north would look like this, with the angle of 60 degrees being located right here. Then it says that he walks 0.5 kilometers due west. So my second displacement looks kind of like that, a little bit longer than the first one. If I place these two vectors tip to tail, you may do that in any order, it doesn't matter which. The resultant then goes tail to tail and tip to tip. So my resultant looks like this green vector here. I like drawing a picture first because it gives me an idea of what that should look like. It helps me check my answer in the end. I will now start to follow along with those 5 steps. The first step says to find the components of each vector. I'm going to label these vectors so that they're easier to talk about. That first displacement, I'm going to call that vector A. And the second displacement, I'm going to call vector B. So if I look at these two vectors, here's A and here's B. I know that A has a length of 0.4 kilometers and B has a length of 0.5 kilometers. You should be comfortable finding components by now. Again, with vector A, we know that the angle it makes with the vertical is 60 degrees. So if I draw its two components, and remember it's very important to draw these components with arrows. That's my y component, and that's my x component. To find the y component, I would use cosine. The cosine of 60 degrees is adjacent, or AY divided by the hypotenuse. I'll even plug in what that hypotenuse is right now, 0.4 kilometers. That means that AY is equal to 0.4 kilometers times the cosine of 60 degrees. The number that I get for that is 0.2 kilometers. It's pointed upward, so it is a positive component. To find the x component, I would use sine. The sine of 60 degrees is equal to ax divided by the hypotenuse, which is 0.4 kilometers. That means that ax is equal to 0.4 kilometers times the sine of 60 degrees, which gives 0.346 kilometers. Now, as we're looking at a picture, is very important. That x vector is pointed to the left. That means it's a negative component. So I need a negative sign here. When you're doing components, you need negative signs for direction, not words. You only need words for direction with your final answer. So now I have an x component for A and a y component for A. So now I'll look at B. B is pointed to the left. That tells me that the x component of B is going to be that 0.5 kilometers, and the y component of B is 0. However, I notice that this vector is pointed left, and so this x component is really negative 0.5 kilometers. I have finished step 1 of adding vectors, so I'm ready to move on to step 2. Step 2 says to add the x components together and to add the y components together. That's actually steps 2 and 3. I will call the total x component Rx. R is standing for my resultant, and that's equal to ax plus bx. That's negative 0.346 kilometers plus negative 0.5 kilometers, which gives me negative 0.846 kilometers. Adding the y components together, I have 0.2 plus 0, and so I get 0.2 kilometers as my y component. Once you get the x and y components of your resultant, you can almost ignore the remainder of the problem. Trying to find the magnitude and the direction of the resultant vector is the same thing as adding these two components which happen to be perpendicular vectors. So I'm going to draw a new picture. I'm going to draw these two components, Rx, which is negative 0.846, and Ry, which is positive 0.2. I'm going to place these two vectors tip to tail, and I'm going to draw my resultant, tail to tail and tip to tip. This x or y component, as we said, was 0.2, and this is negative 0.846 kilometers. You should by now hopefully be comfortable with adding two perpendicular vectors, but in case you're not, we'll go through the work with this one. To find the magnitude of the resultant, we will do the square of 0.2 plus the square of 0.846. I'm very careful when I do this to ignore that negative sign, because if we don't ignore that negative sign on the 0.846, sometimes we forget parentheses and we end up getting a wrong magnitude. When I do this on my calculator, I find that the magnitude of the resultant is 0.87 kilometers. But now I need a direction, because vectors need both magnitude and direction. Remember that you always find the angle at the base of your resultant vector. So that would be the angle I've marked right here. I'll use tangent to find this. The tangent of that angle is opposite over adjacent, or 0.2 kilometers divided by 0.846 kilometers. Again, notice that I'm not using that negative sign. I've really only used that negative sign to draw the picture. Solving for theta gives me an angle of 13.29 degrees. But I'm still not done yet. I have a magnitude. I have an angle, but I need a where. I need to be able to indicate where that angle is measured from. So if I am giving my final answer, I would say that this vector r is 0.87 kilometers at an angle of 13.29 degrees, and this angle is north of west. Again, that angle measurement is touching the west axis, and then it goes above that. Looking all the way back to the very beginning, this green vector that you see on the screen here was my resultant. It looks like it's making a fairly small angle with the x-axis, just as I found with math. I can check and notice that what I got makes logical sense. The green vector here looks very similar to the green vector up top. Therefore, I can say that my answer is logical, box it, and I am done.